Hello mathematicians, welcome to our topic on integration. We're going to start by looking at integration related to finding areas and the basis of integration, which is that it's finding areas by a limiting process. What we mean by this is the fact that we can determine the area bounded by a curve and the coordinate axes by essentially taking that area between the curve and the axes, dividing it up into strips and getting an expression for the area of a particular strip and adding those together. So what we see is that integration is the same as summing infinitely many rectangles, each of which becomes infinitely thin. So it's a limiting process, and limiting in the same sense as finding the derivative was a limiting process where we changed a secant into a tangent in the limit. So what we do is to say that the area under the curve y equals f of x between a and b, which we'll see later on are called the limits of integration, is given by this expression. So it's the limit as delta x tends to 0 of the sum from x equals a to x equals b of f of x times delta x. Now, what delta x is the width of a particular strip, and f of x is the height of the strip. And we're going to add all of those widths by height, which is we know is the formula for the area of a rectangle. We're going to add all those areas of the rectangles up, but we're going to make the rectangles get thinner and thinner and thinner, so that in the limit we end up with a smooth function, under a smooth area under the curve. And so this is referred to as the definite integral. So it's the integral from a to b of f of x taken with respect to the x-axis. Now we'll say much more about all of this later on. But let's have a look at what it means to find area as the sum of rectangles by considering this GeoGebra application. So in this application we can see that we've got a curve which is given by minus x outside of x minus 4. So it's a parabola concave down, cutting the x-axis at x equals 0 and x equals 4. Now, if I decide to break the area under that curve up into rectangles, I could make the rectangles take the upper sum, so that's this, or I could make them take the lower sum, which looks exactly the same here. If I bump up the number of rectangles though, we can start to see the difference. So if I'm going to break the area under this curve up into rectangles, as I said, I could either have rectangles which overestimate the area, so they're the upper sums, or I could have rectangles which underestimate the area, so they're the lower sums. And simply by adding up the areas of those rectangles, I could get an approximation for the area under the curve. Now, in this particular case, with 7 rectangles, the upper sum is 12.73, which is an overestimate. The lower sum is 8.21, which is an underestimate. And the exact area, which we find by calculus, is 10.67. Now, if I increase the number of strips, so therefore the number of rectangles, what I see is that the approximations become closer and closer and closer. So this is the basis of the method of integration. We break the area under the curve up into more and more and more rectangles, and as we do that, the area represented by the sum of those rectangles becomes closer and closer to the actual area under the curve. So if I just go up to the limit of what this particular simulation will let me do, that's breaking it up into 50 rectangles underneath the curve, adding the area of those 50 rectangles, and you can see that the upper estimate of 10.98 and the lower estimate of 10.34 are closing in on our exact value. So obviously if we took that to infinity, so we've got lots of rectangles and they're infinitely thin, we're going to get very close to the exact value. So we've seen that there's a link certainly between the concept of the definite integral and the area under the curve. We're just going to reinforce that by using an area formula to calculate some of these. So if we consider this first one, we want the integral from 0 to 3 of 5 dx. So if I think about what that curve looks like, it's the curve of y equals 5, and I'm interested in the area between x equals 0 and x equals 3. So that's that area just there. Not very well drawn. But that area just there we can see is 3 units long, 5 units high, so it's an area of 15 square units by geometry. Now I'm just going to introduce the idea of finding the area by the definite integral. So this thing here is how we use the definite integral, and we will come back to this. But what we do is we draw up square brackets, we find the primitive of 5, which is 5x, we mark in our limits of integration, 3 and 0, so you'll notice that there's no plus c here because this is a definite integral. And then the way this works is that I substitute the 3 where the x is, so that'll be 5 3s are 15, minus I substitute the 0 where the x is, so that's 0. So that gives me 15 square units. Now don't worry if that seems all a little bit odd at the moment, because as I said, we will come back to it. Let's do I. So for I, what we need is to think about our curve. So we're going to have the curve x minus 4, which is a straight line of gradient 1 cutting the y-axis at minus 4. And we're interested in the area under that curve between 4 and 8. So where does that line up? Well, when x equals 8, the y value will be 4. So we're talking about that area just there, which is the area of a triangle with a base of 4 and a height of 4, so that will be 8 square units. So that's the exact area under the curve in this case. Now, if we do integration, then applying that same method as previously, the integral from 4 to 8 of x minus 4 dx is going to be, so the x will become x squared on 2, the 4 will become 4x. We're going to go from 8 to 4. Plug the 8 into that, so that will be 64 on 2, which is 32, minus 4 8s are 32, minus, plug the 4 into that, so that'll be 16 on 2, which is 8, minus 4 4s are 16. And when I simplify that, that will also give me 8 square units. Now the last one we'll have a look at is the absolute value of x curve going from minus 2 to plus 2. So minus 2 to plus 2, and the height of this will be 2, the absolute value of x. So the area under this curve is that plus that bit there. Now, what do we do about integrating absolute value functions? Well, basically we have to break them up, because we know that the equation for this line is y equals minus x, and for this line it's y equals plus x. But we can also see that there's symmetry. So again, points that we'll consider later on is that we can say that that whole shaded area is twice the value of that shaded area, for example. And what is that shaded area? It's the integral from 0 to 2 of the line y equals x, and we integrate that with respect to x. So that's 2 lots of x squared on 2 from 2 to 0, which is then going to be 2 lots of, when we put the 2 into here, that will be 4 on 2, which is 2 minus 0, so it gives us 4 square units. Now I didn't check this up here before, but we've got 2 triangles, each of which have a base of 2 and a height of 2, so that would give each of those an area of half base times height, which is 2, so altogether by geometry that's 4 square units as well. So just the first one in 11a, it's all we need for this.